So here I've got my car that I need to move it from here, where it is, to over here. I don't know, let's say it's 10 meters away. So, how do I move something? Well, to move something, I need to do some work. And really, what does work require? Well, work requires some effort. So, what would I do is I would give it a push. Give it a push, I don't know. Let's say I apply 50 newtons of force. That's a force, right? So I'm going to give it a push. I've got a force of 50 newtons. And what I'm hoping is that by doing this, this car will end up over here. How much work did I do to make it move that far? Well, it's quite simple. The work is the force times the distance. So, quite simply, in this example, if we took something and applied 50 newtons of force over a 10-meter distance, then we have applied 500 Newton meters of work. Now, I do want to go through the units here for a second. Now, first of all, what is a Newton? Remember that 1 Newton is 1 kilogram meter per second squared. So what we have in this example is we have a kilogram meter per second squared times a meter. So what we have is Newton meters, or we have kilogram meters squared per second squared. Okay? These are what we call the fundamental units of work. Fundamental units of work. Okay? We can still call them Newton meters, but they are typically referred to as joules. Okay? So named after another great physicist. So 1 joule is 1 Newton meter, or it is 1 kilogram metered squared per second squared. If 1200 joules of work are done to move an object 30 meters, what force was applied? So, what do we know? Well, we know that the work done is the force times the distance. So if we want to calculate the force or the distance, it's a simple bit of algebra. So in this case, we want to know the force. So the force is the work done divided by the distance traveled. So the force in this example would be 1200 joules divided by 30 meters. So 1200 divided by 30 is 40 newtons of force. Now, forces should include direction. And our next problem, we'll talk about the direction things are moving. Block, or this box, moves is really important in relation to the work that's done. So if we take this example where we're pushing a box with a force of 85 newtons, and we're pushing it in this downward direction of 35 degrees from there'd be an angle of elevation, and we want to move this box over here 15 meters away. How much work would we need to do? From our previous exploration of forces at angles, we would know that we could convert this into an x and a y component. So the y component would be the hypotenuse, which is the force, multiplied by the sine of the angle. And that would give us our y component. In this example, 48.75 newtons. And if you're not sure how I got the formula on this, it's our trigonomic ratio, so you can go back to some of the previous videos. To get the x component, we would take the force and multiply that by the cosine of the angle. And in this example, that would give us 69.63 newtons. The critical thing to think about is, what direction do we want this box to move? We want this box to move in the x direction. And this y force is actually pushing it down, but the box does not move any distance down. So the distance here is 0. It's going 0 distance. So there is no work being done by this force. Okay, so the Fy is doing no work because it's moving a distance of 0 in that direction. In the x direction, however, it moves 15 meters. So the work, I'll put a W here, the work is the force times the distance that the box moves in the direction of the force. So it's really important that we recognize the direction that the box is moving and what force is applied in that direction. So in this example, the force that we're going to use to do the calculation is not the 85 newtons, but it's the 69.63 newtons of the x. So we would take that and multiply it by the 15 meters. And that's going to equal roughly 1,044 Newton meters, or joule. For any of the problems that we have this kind of situation going on, the work can be defined as the force times the distance times the cosine of theta. And that's a good formula for us to remember as we work through these problems. If I push a box with a force of 123 newtons east for a distance of 18.2 meters and 1,898 joules of work was completed, what angle did I push at? So I've drawn the problem out here, which is always helpful to do. And because it's an angle problem, I'm going to start with my formula of, I keep wanting to go back to forces, my apologies. The work is the force times the distance times the cosine of the angle. What I would do is I would just simply rearrange this, and I would say, well, the cosine of the angle is the work divided by the force times the distance. Now, I know some people like to get into this right off the bat and do the same on both sides. Your math teacher would be proud of you for this. I tend to typically go here and get a decimal number. So I'm going to take my force, which was, I'm going to take my work, which was 1898 joules. Double check that, 1898 joules. Divide that by 123 newtons multiplied by 18.2 meters. And what I'm going to get is a decimal, 0.84785. Go an extra decimal place there. And then when we take the inverse cosine of that, we'll see that we pushed at an angle of 32 degrees. It's very common to have these problems around work connected with our problems around dynamics. And here's an example. Here we have a mass of 1,240 kilograms. It's being moved a distance of 25 meters, and it has an acceleration of 0.58. Now, we don't know the force here. We know that the work being done is the force times the distance, but we don't have the force. But we do know from previous work that our force is the mass times the acceleration. So we could simply take our 1,240 kilograms and multiply that by 0.58 meters per second squared, and we would find out what force was applied to the car. And we would see that the force was 719.2 newtons of work. We could now incorporate that into our work formula, multiply that by our distance, for an answer. Here we have 17,980 joules of work. Once again, we're starting to hit some really big numbers here, into the thousands. So frequently what would happen is this would be recorded in terms of kilojoules. So this would be 17.980 kilojoules of work. More commonly, to solve this, what we would do is we would combine equations together. So going back to our original equation, we saw that our work was equal to our force times our distance. And we knew that our force was mass times acceleration. So we would simply pop that into the other equation and come up with a new work formula that the work is the mass times the acceleration times the distance. Remember that if it's not being moved in the direction of the force, you might need to use that the work is MAD times the cosine of the angle. Just like we combined a work problem with our dynamics questions, we can also combine it with a kinematics question, or both. Here we have an object of mass 25 kilograms moving to the right at 1.2 meters per second, and then it speeds up to 3.8 meters per second over a distance of 18 meters. So what we have is we have an initial velocity of 1.2 meters per second, and we have a final velocity of 3.8 meters per second. We have a mass, 25 kilograms, and we have a distance of 18 meters. So what do we know? We know that our work is our force times our distance. And we have our distance, but we don't have our force. We know that our force is mass times acceleration. So last equation we come up with was the work was the m times the a times the d. But we don't know our acceleration. Now, having our initial velocity and our final velocity and our distance, we can use one of our kinematics equations. How about this one? The Vf squared equals the Vi squared plus 2 times AD. And if you forget how to rearrange these, go back to the kinematics equations. But a little bit of algebra here, I see that the Vf squared take away Vi squared divided by 2D will equal my A. Now I'm going to throw that into my work formula here. My work equals the mass times Vf squared minus Vi squared over 2D multiplied by D. So now I have a formula that I can find my work. I just take my 25 kilograms and multiply that. 3.8 squared minus 1.2 squared times 18 divided by 2 times 18. I've got another question set up here. I'll move that out of the way here. And when we do all this, now we could have done it individually and you would have found that your acceleration, I calculated the acceleration separately, 0.361111 meters per second squared. And we get a final work of 162.5 joules of work being done. But there's something I hope that you recognized, is that both of these equations, okay, I should say both, but this equation had a D on the top and a D on the bottom. Make the math teachers happy. The numerator and denominator both had a distance. Right? Here it is, 18 and 18. And because it's in there, we can simplify this equation a little bit. We can say that the work is the mass times the final velocity squared minus the initial velocity squared divided by 2. Being able to rearrange these equations and cancel out common things is really helpful. And that's where the second equation, second problem here, goes. So this is almost an identical equation to the last one. The difference is this question had a distance. And if you had have tried to find your acceleration, that would have worked in the first one, but in the second question, it doesn't. But let me walk through this again. I know that work is the force times the distance. And I know that the force is the mass times the acceleration. And then I figured out that the acceleration was Vf squared minus Vi squared over 2d. And I'm going to pop that into that equation. Let me just keep this in a different spot here. So if I take this and put it in that equation, I have that my work is, and I'll leave my mass in green here, and I'll put my acceleration, Vf squared minus Vi squared divided by 2d. And then it's multiplied by d from my original equation. Okay, so once again, I have a d here and a d here that can cancel out. So what I'm left with is work is mass Vf squared minus Vi squared divided by 2. Or you might even see it written as 1/2 m Vf squared minus Vi squared. Okay, so we can just take our numbers now and pop it in there. 38 kilograms. And our speed's 4.3. I'm going to do the units out and everything in this. That squared. Take away my initial velocity of 1.4. Oops, 1.4 meters per second squared. And we're going to divide. Oh, we got the half out front. Okay. I'm just going to look at the units here first. Let's just look at the units. Here I've got a kilograms being multiplied. And in the brackets, I've got meters squared over seconds squared taking away meters squared over seconds squared. And since those are the same units, they just come out of there. So this is going to give me a kilogram meter squared per second squared. And we know that that's a joule. So now if I take the numbers and I take half of 38, let's see, that's 19, and calculate this out, I think that the answer I get here is 314.07 joules of work.